Good afternoon and good morning, everybody. I hope people can hear me. I'm new to Zoom, so that's something we have to explore. So if somebody can hear me from the attendees, please give a small notification, because then we know at least that element is working. I can hear you. Good. That's a good sign. It's now 1 minute past, so I also don't want to consume too much of the time. So we start, and people that will join in later will miss a small part of the presentation, and they can also connect, of course, next week. First of all, thank you for joining this webinar around the anisotropic optimization software developed by ParaMatters and Covestro in collaboration. Today I will not be alone. I will be supported by Michael Bogomolny, the Chief Technology Officer of ParaMatters, as well as Johanna Driese, who is scientific researcher at the Composite Technology Center, an Airbus company. Those two gentlemen will assist me today in telling you the story, what has been developed and what we've been validating, and we are bringing to market in a beta setup. One of the first things I want to mention is that this webinar will be recorded. So if you don't appreciate such a situation, then it's the right moment is now to step out, and we could connect outside this webinar if you would like to hear and understand what this technology is about. But for us, of course, most efficient to tell it in this way, and also to be able to use a recording to share with other people which haven't been able to join this webinar today. So I will continue now, and we will start the session and the webinar. The agenda, we will shortly introduce the three different companies. We will talk about the background and the background why the anisotropic optimization software was developed. We will do a small demonstration of the software to give you a feeling how the interaction would be, how the flow would be within the Cognicad software. We will explain call it alpha test, which has been performed by CTC GmbH, an Airbus company, on applying the software in their development process to really see what the capabilities were, to learn from it. It helped us in ParaMatters Covestro to develop the software further to make sure that it fulfills better user requirements and demands. And that also led to this beta stage where we want to invite other customers and users to come forward to try it out and to make sure that we really make the final step towards commercialization. We'll explain a bit about the beta program, and last but not least, some questions and answers. We expect a total webinar presentation to take about 30-35 minutes, meaning we have 10 to 15 minutes of questions and answers. If you have questions during the presentation, you can type them into the notification area where you can give messages, or you can, of course, write them down and ask them when we open up for questions and answers. So if we have a small introduction, Covestro, it's a chemical company. We are leading in the world of polymers. We are a bit over 10 billion in sales, about 18,000 employees. So we are quite a nice and sizable company. We have about 50 production sites globally, and we really move close to customers and partners to make sure that we bring innovation to market, which makes sense. And bringing innovation to market, we do that with 1,500 colleagues. And especially our purpose is to bring a brighter world. So preserving the environment, advancing society, and creating value for the people and the partners we work with. I think it's also good to tell a bit about circular economy. We committed as Covestro to be fully circular, to really make sure that we deliver a more sustainable world for generations to come. And that's something where also this kind of software and this kind of collaboration will help to accelerate on that path towards a more sustainable future. Here I want to give the hand over to Michael Bogomolny, who explains more about ParaMatters.
Thank you, Bram, and good morning, everybody. ParaMatters is a California-based software company. We were founded in 2016 with the goal to deliver very effective software tools to automate and make design and manufacturing process productive. So we developed very automated and effective tools for design workflow, taking users in most productive way, shortening design cycle in the field of design for manufacturing, supporting variety of materials, and as well as additive manufacturing processing of how we take design for the next step to the manufacturing, all in most automated way, leveraging cloud computing. And we were very excited to join this fruitful collaboration with Covestro to develop tools which we are happy to talk more about in this webinar. Looking forward for it. Bram, you're muted. I think Jorne from...
Jorne.
Yeah.
Yes,
can you hear me now? I think now it should be fine. Or not?
Yes, Jorne, yes.
Okay, all right. So also a hello from my side. So my name is Jorne Driese. I'm working at the Composite Technology Center in Stade. It's located in the northern part of Germany. And the CDC is basically a techno center from Airbus. So we're 100% subsidiary of Airbus, focusing on the development of innovative technologies for the industrial and automated processing of composites, and especially for CFRP. Throughout the year, so from the founding of in 2001, we have expanded also our fields of expertise towards diverse fields of innovation, as for example, automation, assembly, cabin processes, as well as education. And this we deliver for Airbus internally, but also to external partners.
Good. Thank you, Jonas. So, Michael, you will explain a bit more about the anisotropic optimization software.
Yes, please. So, first of all, about ParaMatters suite of solutions. So, we developed the software suite of tools called Cognicad, which have very automated generative design and manufacturing workflows. And the idea behind the tools was to simplify and accelerate the design process by leveraging of most advanced algorithms and cloud computing to make our users successful and to benefit to the design and manufacturing flows. So the major idea from developing such tools is to if you're familiar with current design to manufacturing flows, they require a lot of iterations and manual interruption to the process, which makes design cycles very expensive and long, and automating very labor-intensive parts have a lot of benefit on overall design process. So this is the suite of solutions that we have developed, and we can dive deeper into the anisotropic part. So first of all, we want to understand, I want to explain what this tool is not and how different the anisotropic topology optimization. It's not standard traditional topology optimization with isotropic materials, and we will talk about isotropic materials which have the same properties in all orientations. And it's not a lattice. Lattice is not an isotropic topology optimization. What we have developed is something completely different. It's more related to what people experience with composites design and optimization. First of all, what's the difference between isotropic materials and anisotropic materials? Isotropic materials, these are materials which have similar material properties in various orientations. For instance, this will take metal, and we will try to make tests, pull it in direction X, Y, and Z. We will see that material properties in all these orientations are more or less the same. The challenge becomes when we deal with materials like composites, which have given fiber orientation, and along the fiber orientation, stiffness and strengths are hundreds of percent, sometimes orders of magnitude stronger than perpendicular. At the same time, composites have very high strength to weight ratio, which can save a lot of weight, but we have to design structures on a very smart way using anisotropic materials, meaning we have to place them in the right place and orient the fibers in the right orientation. Now, given additive manufacturing capabilities, it gives us much more freedom to apply and align materials in various orientations, give really tremendous freedom also to place material where it's only needed. So there are a variety of materials today on the market which have fiber reinforced filaments and allows generation of very lightweighted structures. And we felt like there's a big gap in the market. There is no design for additive or generative design solution which can take anisotropic materials into account and push those designs directly to manufacturing, because designs are very complex and manufacturing processes becoming to be complex, and just there are no tools to automate this design to manufacturing flow. So this is exactly the gap that we closed in this development. So first is to just develop tools which can, based on physics, finite element, and topology optimization, can take anisotropic materials into account to find the right material placement to carry loads on the most effective way, to find the most optimal material distribution and orientation. And in order to automate the manufacturing workflow, software is also able to generate support structures, brim, and export the design in the universal G-code format, which can be directly taken to manufacturing. So if we look at the traditional industry workflow, it includes many steps, and also those steps are quite labor intensive and very iterative. It starts with modeling preparation, creating available design space, and then there is a conceptual optimization process which requires several iterations, and then there is a step which you need to make interpretation of the conceptual design, also quite labor intensive process. Then it requires another validation and rerunning analysis in order to get to detailed design. When detailed design is done, then there is a need to position, to generate support, to slice this model before manufacturing. So there are many steps which are very manual, labor intensive, and iterative. So what the software that we have developed, it's basically consolidates the most labor intensive pieces into one automated step. So instead of months, the design cycle are shortened to tens of minutes up to a few hours. And what we do, we shrink the design to end manufacturing workflow. Yeah. And so now I would like to run a short demonstration. So this demonstration will consist of two parts. The first one is the preparation of how we prepare model for optimization and manufacturing. And the second, we will review the results. Before starting it, we always assume that our users use any CAD system, and from any CAD system, you can export your available design space. So when we design a part, we have interfaces where parts should be mounted as a part of the assembly. So those interfaces should be preserved, untouched, and we create a design space, maximum available place where part can live. We do it in any CAD system and import as a step assembly into ParaMatters environment. So once part is imported into ParaMatters software, Bram, if you can run the video, please. So once we have this assembly, once we have this assembly, there are several steps user must take into account. So first, they need to define material properties. And keep in mind, those are anisotropic materials properties. You can see that orientation in X, Y, and Z, they are different. It requires from user to have the right material definitions, and I'm sure Bram from Covestro will talk about this. Second, we assume that X, Y, it's a plane where material is deposited, and Z is the orientation, build orientation, so user can rotate the model on the build plate. Then users need to classify in the assembly what is a design space and what are the keeps in region, the regions that need to be preserved and cannot be removed. Now, loads and boundary conditions are applied on these non-designed regions. And when we support variety of loading conditions, static and vibration load cases. So for statics, we need to define the boundary conditions, how part is fixed against movement in various direction. Second, we apply loads, and can be, as I mentioned, variety of loads. Can be forces, can be moments, pressure, acceleration loads. You can see that in some cases, loads can be applied via remote points, which are very useful for variety. And users can define variety of load cases, can be several load cases. You can see that in this case, which is typical for aerospace, we had 11 load cases. And the next step is to define goals, what we would like to achieve to maximize part stiffness or to minimize mass under stiffness constraints. So here we wanted to maximize the stiffness and use only 8.85% of the material, meaning we will remove 92% of material. In the last step, users define finite element resolution, minimum feature size to ensure the manufacturability of the part. If there is a need to enforce symmetry, there is a way to define planes of symmetry if you want part to be fully symmetric, even if loads are not symmetric. And next is to define the manufacturing parameters, because as I mentioned, the result will be G-code. And as a G-code, we want to be fully agnostic to the market, and we define universal G-code parameters like layer thickness, filament diameter, speed of print, and so on. Plus, in order to make this part manufacturable, in FFF, FDM technologies, we need to have also support structures in brim, and those parameters also users can define in preparation. So basically, what you see, we imported CAD, we applied CE, FEA settings on CAD. We don't really need to deal with mesh here, and we also defined. You see these six steps of defining material, design space, loading conditions, and manufacturing parameters. So geometry, analysis, optimization, and manufacturing are taken into account with this one flow. And from here, users hit button design. And after you will see it's running, it will running on the cloud typically, but we also have local version for customers who cannot use cloud for various restrictions. And as a result, users, after design is complete, this is what they get. You can see the ghosted model is the original model, and the green is the optimized structure. The advantage of ParaMatters technology is that you obtain clean, nice output right away. There is no need to involve many model reconstruction, shrinking, smoothing, and reanalysis. And of course, the results are not just nice shapes. They include the finite element validation for each load case, and we can visualize how parts behave under these load cases. And of course, it includes the stress distribution. Since we talk about anisotropic materials here, we include Tsai-Hill criteria. We also can introduce the reaction forces on boundary conditions. This is what we get. But what is important to mention, since we talk about anisotropic materials, we need to know how we are going to manufacture them and to deposit material, to extrude material in the right orientation to preserve the optimal angles. And from those, we create this G-code, and users can review the G-code. If you can, in a minute, zoom closer, you can see that layer by layer, the orientation of the fibers changes according to the FEA analysis, right? So the optimization determines the right material distribution, and we need to preserve it. That's why we export it as a G code, and you saw that it also exports the rim as well. And as a result, if you can, and as a result, user can download not only geometry, STL, and STEP. They can also see the G code, and we even print how much material goes to the part, the volume of the part, how much material will be basically wasted as support structures in brim, and what's the total amount of material. And by G code parameters, we also know what's the printing time. So this is quite a big bracket, and printing time is quite extensive in this specific case. But again, I wanted to mention that software in one run is doing the finding the right shape, validated by an FEA simulation. It exports the geometry if needed to be as a STL and as a STEP file if it needed to be documented in CAD environment. And for manufacturing, we export the G code, which also includes brim and support structures as one. So we see that we automate the workflow from design to manufacturing.
So thanks for that explanation, Michael. And now we'll go to Joran to explain a bit more about what we have done and how ParaMatters Cognicad software can help them in their daily operation.
Yeah, thank you, Bram. I'm happy to share some of our experiences so far. So a little bit of a background why we were interested in exploring the software developed by ParaMatters is that one of our research areas in the CDC is with additive manufacturing. So we have an own production center available where we can really focus on each step in the end-to-end cycle. So really from the design and sizing of geometries and parts into the production until the final post-analysis and validation, and vice versa. And we have diverse systems available, which can, for example, build prototypes, small production series, but we have also more industrial machines and more complex systems, for example, robotic end effectors, where we really focus on material screening and process development. In the next slide, you can see some of our showcases to give you an idea what we work on. So on the top left is a bracket which is currently milled out of aluminum, where we made an alternative design using continuous carbon fiber composites. On the bottom left, for example, is a demonstrated part where we used electronics within the printing process. So for power transfer and signal transfer. And for example, another one on the bottom right is within medical applications. And in each of these applications, there's some sort of anisotropy available. And what we noted in the last years is that the design and sizing, so the engineering time to develop such parts, to create the print pads and so on, it takes quite a lot of time. We need different tools, and therefore we were of interest. So what we did in the next slide is that we looked into a use case. So we looked into the Airbus A350 program and identified a structural bracket, which we think it was a feasible use case. So the reason why we chose this is because the bracket has a low amount of parts per aircraft, and each bracket is not like the other. So meaning that each bracket itself has some small design changes. So it's a very customized product. Of course, in aerospace, it needs to have a low weight and high stiffness, and the bracket has been designed or needs to be designed with 11 different load cases. So in the end, what we did with the ParaMatters software tool in the next slide is we analyzed basically two things. So in the first thing, we analyzed it via the ParaMatters Anisotropic tool. For this, we used Ultim 98.5, which is our standard aerospace material printed using the FDM technology. And in a second trial, we used the Anisotropic, so the ParaMatters Anisotropic tool, to print using Novamid, which has 10% of carbon fibers included in the filament, to create the Anisotropic design. So both of the designs have been developed or iterated with the same amount of requirements. So exactly the same boundary conditions, exactly the same loads and so on. And we try to approach a similar weight for both components. In the end, as you can see in the slide, is that we received, or in the end, a compliance improvement of 39%. And what this means is that almost the stiffness of the anisotropic variant compared to the isotropic variant doubled. And for this, we of course then have stronger parts. This is being generated, if you look into the next slide, yes, basically due to the infill. So in this picture on the right, you can clearly see how the infill is created for the anisotropic bracket. So really aligning the fibers with the load path of the structure. So this is not something comparable to the original slicing software, which maybe take like a ±45-degree angle infill or concentric infill. It's really aligned with the load path of the structure, creating then these benefits. So what currently is ongoing on our side is that we are looking into, okay, now we have these benefits from the design. Are they also representable in practice? So what we did is we printed the Ultim variant for the isotropic design. We printed the Novamid variant for the anisotropic design, and currently are suscepting them to load cases for the bracket and seeing whether the benefits really apply in real life. So that being said, what we concluded so far from the software is that, as you can see from this bracket use case, we really get a weight potential taking into account this anisotropic behavior, both in the design and in the manufacturing process. But further all, what we see, especially in R&D, if you're designing parts and you have to make multiple iterations and use different tools, this takes quite a lot of time. So by using the ParaMatters tool, where the whole design process and integration for manufacturability is integrated, so you directly get a G-code out of the software which you can put in your machine and print, we can really reduce the development times. And that's mainly what we concluded so far from this, let's say, alpha program, what we did in collaboration with the ParaMatters and Covestro. So this concluding, I can give back the word to Bram.
Thanks, Johanna, for your explanation and how you are benefiting from the technology. So to capture again a bit what Jordan mentioned is, so if we take design analysis on the equivalent loads and use cases, we can optimize design orientation and print part for the best performance to weight ratio and go to a first time right, saving cost, production efficiency, and reduce carbon footprint. So really true optimization for anisotropic production technology. So really taking fibers and reinforced materials and maximize the potential of these kind of materials. So in the middle, what you see is an anisotropic bracket. The comparison that has been done by CTC is to compare similar on weight, but what if we compare on the same deformation? And then you see the consequence of printing an isotropic material, so an Novamid ID1030, which is unfilled. What is the weight of such a bracket, and what is then the consequence? So this has the same deformation, it has the same performance application, but of course the weight is significantly different. But that's not where it stops. So if you start putting this in numbers, if you would put a standard isotropic solution, it would take a print time of 65 hours. It has a weight, including brim, including support, of more than 1 kilo. If you then compare it to an anisotropic solution, you're printing 35 hours, and that's a significant benefit. So it's not only about the weight, which reduces to 454 grams, including the brim support. It's also about production time. Your machine park, you can print the double amount of products in the same amount of time if you compare, if you would print one isotropic solution. So these are multiple benefits, and of course reducing significantly in cost for the user. And that's where we see really the benefit starts catalyzing a kind of snowball effect, what you can achieve within your production and development process of new products and designs. Based on that learnings, and based on the fact that we want to make sure that it fits the needs of the market, we want to expand our beta program. And also that's why we have this webinar to look and see into the interest that's in the market, to help us to make sure that we further increase reliability and performance of this product before we go to commercial. So we really want to have the latest 5% of improvement that we potentially need to come out from such a beta program. So we are looking for beta customers for validation of new technology, manufacturing parts using anisotropic materials, and to testing these manufactured designs in your own circumstances, your own facilities, because it's not about us producing for you, it's about you being able to use technology in your benefit and being able to reduce your development time, increase your performance, and reduce costs. Therefore, we have the beta program, which is the ParaMatters Cognicad Anisotropic program, which runs from October to December, so a 3-month period of time, where we can have access for 4 users, and each user has 250 tokens. If you look at the case that you just saw with Airbus, that case, which is a very high load case, because it has 10 load cases, it consumes about 100 tokens per design run. But typically, we see that you are on the level of 30 to 40 tokens to do design. So this is quite a huge amount of designs you could try out and test with. We will provide, if interested, Novamid material, which is the material that we validated we are validating the software with. Why is that? Because from Covestro perspective, we have a fully anisotropic characterization done of this material according to the performance for additive manufacturing. So that could be provided to the beta program users, 2 times 1 kilogram spools. If you're interested, of course, we're going to have a dedicated training to make sure that you have a flying start, how to prepare your file, which can be uploaded into the Cognicad software, and how within the Cognicad software you can do the right definition of loads and forces and choosing materials and these kind of things. During the program, there will be of course, again, interaction to make sure that we understand what the benefit could be, but also what maybe are improvements. So that's why we at least propose 2 times 1 hour goal to make sure that we share and understand. And this package will be offered for $6,000, which is a significant reduction of what the cost would normally be. In the future, it will be what we're looking into now as a token-based solution. So meaning you would have a small setup cost for your license, but afterwards you could purchase the tokens required to run your optimization. And we believe that that's a convenient way to have access to a very, very helpful tool and software, where you don't want to be a high license, but have rather use and pay for use versus high license fees. What we have to, of course, to make clear is that it's a beta program, it's not a commercial product. So it's certain things could happen, certain things could result in a result that you didn't expect. And that's something we want to explore. And that's also the reason why we do the beta program. The intent is to provide you the full benefits and explore how this can help you in your daily operations. And we want to learn if we still have to make improvements or it's good to go. We believe, based on the alpha program, that we are quite close to a solid and robust solution. But of course, we want to put that to the test with a bigger group of users. There are some boundary conditions in where to apply it or which equipment does it work. At this moment, we see that the equipment that it works best with is open source FFF equipment, where you produce it using relative mode production. For sure, in the future, we will extend it, but we have to start somewhere. And this is something we have now a good understanding of what the benefits and limitations are. The Cognicad software is material agnostic. So at this moment in the library is a Novamid material, but if you want to apply another material, if you know the anisotropic parameters of the characterization of that other material, you could change the values and you could run an optimization for another material than a Novamid. But that's also why we are opening up to make sure we grow that library. So it's not only connected to Covestro. Covestro, we saw as Covestro a gap in the market. Together with ParaMatters, we developed this piece of software, and this should be benefiting all anisotropic materials and not only Covestro anisotropic materials. So this would be a material agnostic solution which can be used for any other material supplier than Covestro, as long as an anisotropic characterization is available to be deployed in the Cognicad software. If you want to do validation in this period of time, we advise you to use an Novameet ID1030, which will also be provided to do a test, because the material is correctly characterized. The software, we know that it works, and we've seen the first prints coming out of it. So we know that those steps are best under control. One of the elements is, at this moment, it's a cloud system, Cognicad. So we want to make you aware. So it's good to test if you're not behind a firewall, that you can reach it, that you can use the software. If there will be an issue, we have to look into what the options would be. But at this moment, we want to make you aware that's a cloud-based solution, which you normally could reach. But it can also be that you're restricted by your organization. That's something we cannot conclude without knowing your situation. It's a program that will be brought under the wings of ParaMatters to the market. They are the commercial entity and the commercial organization that brings a solution. If there's questions specifically to Covestro, more than willing to help, but this is something that Covestro lends to the market as a solution. And therefore, information, or if more information is required, that can be posted towards ParaMatters. Based on this information, and I think that's what it comes down to. We believe we made a small step. It's a huge gap that we see, but we made a small first step by offering this solution for FFF. We see much more potential to the future. So that's also something where your input and your suggestions are very welcome to come forward with, how this solution could grow towards the future. But we don't want to develop everything in one go. We want to start small, but then based on feedback and market need, develop fast and scale fast to make sure that we can bring much more benefits of reinforced materials to the market and reduce our carbon footprint, make stronger parts, make lighter parts by which we can drive further, fly further, sail further, whatever you want. But we believe this is a very important step to make sure we have a more sustainable future in front of us. Based on that, we want to open for questions and answers, and we hope that we could entice you and interest you to join this program.
Thanks, Bram. I see some questions coming in, and we can potentially address them now. The first question is, Cognicad is a cloud or desktop app? So Cognicad is available both as a cloud and as a desktop. For the beta customer, we prefer to work with the cloud because it's easier to support. The final product will be available in both versions, cloud and desktop Windows install. And I see another question is coming. Do you support Markforged printers? They are encrypted G-code. So we work with several equipment manufacturers, and some of these manufacturers have closed system, which we would need collaboration from their side. We had few discussions with Markforged. I hope we will start working soon into enabling of this. Like another question.
I think that's a fair answer. So maybe to add to that one, at this moment, Rosie said the boundary condition is open systems. If it's a closed system, that's also why we open up this beta program to make sure that equipment manufacturers would say, I want to benefit from this technology, that we ensure that we have a connection towards their, an API connection towards their closed system. But that needs development, as simple as that. So we are fully open towards that kind of route, but that's something that requires more work together with those equipment manufacturers.
And I would say, if you give feedback to these equipment manufacturers that you would like to have such a solution aligned, they will feel more, let's call more pressure to do this. Another question I see, despite the software is machine agnostic, do you plan to create a program to integrate Cognicad into OEM ecosystems? Yeah, we have discussions with big equipment manufacturers. We do plan. The answer is yes. I see another question. The output is a G code. What control over printing parameters do I get? So the control parameters are, if Bram, you can open that video, we can just look at it. The previous one in the setup. Yeah, go to the end. A little more.
I'm playing it. Let me see if I can pause it.
Okay, yeah, here. So we have, you can define the layer thickness, bed width, number of outer contour to have good surface quality, printing time, filament diameter, extrusion multiplier controller, and number of, if you include brim, number of brim contours, as well as build plate dimension and the origin. So those are, we found out those are the minimum requirements are needed. So for open system, it works well. Regarding the support structures, Bram, if you can open them. So the filament diameter, and we are adding more, but those are the minimum necessary ones to make part printed. And so far it worked very well. Bram, as for support structures, if you can also push to the next one. For the support structures, again, speed of filament retraction is defined, length of filament retracted, the overhang angle, the density of supports, and for better removal of supports, there is a parameter of offset from the part horizontally. So.
And that means that you can change all of these settings towards your own preferred settings, what you apply. So we in the end, what we want to have is a kind of library of different equipment, and by which you will get a pre-setting. So if you just want to use what is being advised, it can be done, but you can overrule any of these values by your own knowledge and your own expertise to change things. So. It's something that should help you and not prevent you from execution.
Yeah. So I see another question. Does the anisotropic optimization generate a toolpath featuring lamination? Adjustment layers of materials are oriented differently when it is favorable. It would seem laminated materials are optimal in certain region, especially when there are multiple load, for example, regions. So I will, if I understand the question correctly, in traditional laminated composites, when you take prepregs, you basically have fixed orientation in all the plane. The advantage of additive that you can change orientation of the material alignment according to the optimization. So if you could see, Bram, if you can run this video a little back, when we see the G code, basically in plane, even each layer, we can change orientation. Oh, sorry, it's a result video. So the advantage of this one is that we can change orientation wherever is needed to get the maximum orientation. So you see layer by layer, as we are moving, even in plane, we can change orientations. So we have a full freedom here of orienting and optimizing material placement, which is I would say huge, right? Because current traditional composites manufacturing are really limited to given prepregs orientation. So this is a big advantage of this. I hope it answers questions correct. The next question is, with extrusion passes following the load passes, how do you ensure that the material is not overfilled in areas where the passes follow close together? Perhaps like you show really need local extrusion control through the lens? Yeah, well, it's a good question and it's a challenging problem. And we solve this on the level of algorithms which generate the tool passes and calculate the extruded material. And the amount of extruded material in, let's say, in areas where there is sharp curvature change, quite challenging. So we calculate the extrusion of material on a different way such that it will fill all the gaps. And it works quite well in areas where there's a super high curvature. It can be some minor gaps. This is what we are working on, closing this gap. And that's why we continue this development. But so far, it looks like we achieve very good surface quality and filling of the gaps.
Do you need special prints to print anisotropic parts? No. Normally, you should not. It, of course, depends which material you apply and what the requirements of that material if you need a specific printer. So there are certain materials which are benefiting from a closed build chamber, but other materials are not affected by it. So it's not that it's agnostic, and it is not restricted by the printer. Of course, if there's not an open code accepted and you have a proprietary code, then it requires work to make sure that the generated G code is translated into the format that the printer can accept.
Yeah.
If anybody has questions, you can also open up the microphone and ask live. There's no issue. So you don't have to type everything. You can also.
I see another question came. Is the layer slicing only planar? Right now, yes. If I understand the question correctly, so yes, it's FFF FDM technology when we print layer by layer. Yes, in the future, we plan to expand this from 2.5D to full 3D.
I also see in the chat which 3D printers can be supported. As you said, open printers at this moment with a relative mode, we see are the easiest one to adopt this one. But in the end, any printer should be able to execute it because it's just a machine code that's provided, and that could always be translated to a path for each printer that will be out there. We are only considering FFF technology. Yes, at this moment we only consider FFF technology. That's just to get, we see an issue, we see adoption in the market, and where you see a lot of requirements is for sure in the filament. It's easier for designers to start with versus the large machines and these kind of things. But it should not stop there. So I think what we also say is think big, start small. We start small with only FFF open, but of course thinking big towards maybe granulate extrusion. You can also think about powder kind of direction, but that has other requirements and other things to take consideration because it's not always fully anisotropic. So those are things that of course could be on the table. But we had to start setting a first stepping stone to bring this forward.
Also, Bram, at this point, it should be mentioned that obviously any technology that uses a G code and creates anisotropic material can be used with what you have prepared, right?
Yes. Yeah, but of course, everything what is new and not been seen, that's something that requires some potential development. But we try to make it as scalable as possible to adopt different things. A comparison you know with anisotropic and isotropic, can you please explain the difference? There's a material from Covestro called Novamid ID1030. It's an unfilled material, and there's a filled material, and that's a difference. So we have one which doesn't contain carbon fiber, another one contains carbon fiber. And that's what we use to compare what is the effect of having a filler in there and positioning that carbon fiber in the optimal direction, what the benefit could be to unfilled material. do users can help to find the best part orientation? And Michael, I believe it's good for you to address this one.
Yeah, that's good question. Look, as you change orientation, actually, this is a study that CTC Airbus have done, 11 load cases, and in some orientations, some load cases are critical. On the other orientation, different load cases are critical. So definitely, part orientation on the build plate will have an effect, and Airbus colleagues ran a study of optimizing part for various orientation and found the best orientation. Maybe Inga here on the call can provide a little more information, but definitely orientation matters. And in the future, we planned to include the optimization of the orientation as a part of the workflow.
Yeah, should I give some more information on that?
Yeah, please, Inga.
Sure. To let you know what we did so far is that we changed the rotation within the software and did a whole 360-degree rotation study, let's call it that way. And we have the opportunity to export a report of the different values of compliance and stress, etc., of the resulting model of the optimization. So with all the values we could process, and we could evaluate the results and find the best orientation.
So at that moment, this is the help that we can provide. Or maybe this is the help that we can provide today. But as Michael said, we would like to orientate and give options for orientation. But at this moment, it would be the user to decide how it's orientated, or to make a study to do, for instance, every 15 degrees rotation, and do an optimization run at that location, then compare the results. But of course, that's quite that's more labor intensive. But that's today where the status of the software is.
Well,
any more questions? Anything which was not addressed, or what you missed, or and responses on the software itself, and how, if you believe it addresses a need that you have.
I see no more questions, and I think we also a little out of time. I thought it was great conversation.
So yeah, I think to conclude, maybe it's still have to go to. We will share with you if you're interested in participating and joining such a program. Please reach out to us. We will make sure that you will get the email address where you can reach out to, and we can discuss such a program. So we hope, yeah, we look forward to hear from you and see if we can collaborate in bring this kind of technology further and really